All right, so good day, was know. Yes, as mentioned, this is the second part of dicarboxylic acid, and then this will see us to completion of this topic. Good. So, a synthesis of dicarboxylic acids. Now, we are saying that a number of straight chain aliphatic dicarboxylic acids in their derivatives occur in nature. However, isolation from natural substances has no commercial use. So we are saying that even though we can get some of these compounds from nature, we cannot get the amount we want if we want to isolate them in nature, or maybe too expensive. So commercially, we have to synthesize them. We cannot depend on the natural sources commercially, right? Now we are saying most dicarboxylic acids are prepared by adaptation methods used to prepare monocarboxylic acid. So the same knowledge we apply it here. Good. Now, synthesis. So the first synthesis they have given us is oxidation of primary alcohols, right? So now if we have diol, that is a compound having two hydroxyl groups, an organic compound having two hydroxyl groups. Now we can oxidize it to get two carboxylic functional group. So we can oxidize the primary alcohol to carboxylic functional group. Very simple, right? That's the first way to make it. Then on this, at this point, we have to know the different oxidizing agents available, because if you don't know them, it will become very difficult for you to know when there's oxidation occurring. Next one. Now it is still oxidation, but then this is oxidation occurring with cleavage, right? So oxidative cleavage, right? You are using nitric acid, which is a very strong oxidizing agent. So what will happen here? Very simple. Right. Usually I want to explain the buildup that will lead to the product formation. The buildup that will lead to the product formation. So yes, what will happen here is that this bond will break. So this bond breaks. This carbon would be COOH. So this is already carbon. So OOH here. Then this carbon will have OOH, right? So double bond O, then OH, double bond O, then OH. So that's what happened here. You realize that there are 6 carbon here. There are still 6 carbons in this chain, right? But then the terminal carbons that were involved in the double bond have been converted to carboxyl groups. That is what has happened. Oxidative cleavage. Very simple. Very simple. Good. The next one, we have formation of dicarboxylic acid from dihalides. Dihalides. So we have an alkyl group with 2 halogens, right? Then we can change the dihalides to nitrile, so dinitrile group, right? And then after getting the dinitrile group, we can heat it in the presence of aqueous acid, and that will give us our dicarboxylic acid compound. Very simple, right? Very simple. So we took it from the dihalide using the sodium nitrile, and then water, right? And after that, we heated it in aqueous acid, and then we got our final product. Now, this is showing us how we take it from dihalide. But then when you take it from dihalide, we have to pass through the dinitrile. The dinitrile can also be a starting material. So in the next instance, we are talking about just hydrolysis of dinitrile. We can do it in a base, we can do it in an acid. So this is OH minus happening in the base, right? Good. Now what will happen is that the nitrile group here will be converted to yes, it will be converted to carboxyl groups, right? Good. Now we can do it in the presence of acid and water, that's aqueous acid, right? To get our dicarboxylic acid. So very simple, right? Now the next instance is taking it from the dihalide, right? So we put our nitrile groups or cyano groups there, and then we acidify to get our dicarboxylic acid. Very simple. Very simple. Good. Good. Now we can also decide to oxidize alkyl groups, right? Alkyl groups on a benzene ring. Now, if you use a very strong oxidizing agent like KMNO4, right? Or this now, the whole of these reagents are reacting to give you chromic acid. So instead of writing this region, you can just write chromic acid, right? You can just write chromic acid. So all these are reacting to give you chromic acid. And that's what's happening, a very strong oxidizing agent. So when it reacts, it will convert the alkyl groups. Now, irrespective of the length of the alkyl group, once it is not the carbon attached to the benzene ring, that we call it the benzylic carbon. If that carbon is not tertiary, then if in the presence of a very strong oxidizing agent, it will be converted to what? Carboxyl group. So that is what has happened here. The two alkyl group, irrespective of the chain length, have been converted to what? Carboxyl groups. Carboxyl groups, right? And then we have our terephthalic acid here. Very simple. Good. Very simple. Very simple. Very simple. Very simple. Good. Now, synthesis. So we are still on this. Then the last one, we are talking about the effect of a strong acid like nitric acid and then a weak oxidizing agent. So the strong oxidizing agent is the nitric acid, and then the weak oxidizing agent is the bromine liquid, right? On aldose, right? Aldose is sugar, an aldehyde sugar. So the aldehyde sugar has an aldehyde functional group here. It has a primary alcohol functional group too. Now, in the presence of a very strong oxidizing agent like nitric acid, it can oxidize both the aldehyde and the primary alcohol to get your aldaric acid. Now, the aldaric acid here is a dicarboxylic acid, right? It's a dicarboxylic acid, very necessary to note. Very necessary to note. And then in the presence of a very weak oxidizing agent, it can only oxidize the aldehyde functional group. It can only oxidize the aldehyde functional group. Can only oxidize the aldehyde functional group to form aldonic acid. So that is mono carboxylic acid. Good. Now, an exercise for us to try. So they are saying a hydrocarbon with molecular formula C9H12 yields phthalic acid as the only product, right, on oxidation. We should give the structural formula. Now, the first thing is that we should know the structure of phthalic acid, because if you don't know phthalic acid, we cannot draw. So phthalic acid is like this. That's the normal phthalic acid, right? It's like this. So COOH, O2 COOH. Good. So that is normal phthalic acid. Normal phthalic acid. Good. That is normal phthalic acid. Good. Now we can attempt solving the question, but then we cannot oxidize to get benzene ring. It means the starting material should necessarily have a benzene ring. So we can draw our benzene ring, right? So benzene ring. Good. Now benzene ring will take 6 carbons from here. It will take 6 carbons. So we'll be left with 3 carbons. The 3 carbons, we can make them alkyl group because we know when you oxidize alkyl groups with strong oxidizing agent, we get carboxylic acid, right? So we can make the 3 carbons CH3. So we have consumed one. And then the next carbon will be CH2, C2H5. That's CH2CH3. So we have consumed all the carbon. Now, if you count the hydrogens, they will also fall in place. Exactly. So we have used 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons. If you talk about the hydrogens, there's one hydrogen here, one hydrogen here, one hydrogen, even though we don't draw them in the skeletal structure, one hydrogen here. If you count 4 hydrogens plus 3, that's 7 hydrogens, plus 5, that's 12 hydrogens. So that is all for that one. Very simple. Very simple. Now, another exercise for, okay, so the answer is here. Reactions. So the reaction they will undergo. Right now, we are saying in general, dicarboxylic acids show similar chemical behavior and reactivity as monocarboxylic acids. Good. Now, in addition to the reactions of typical carboxylic acids, there are dicarboxylic acid that undergo reactions that are only possible because of the two carboxyl groups, right? And because these are located in a particular way. So we will talk about the reactions which are peculiar to some dicarboxylic acids. Now, the first one, effect of heat on dicarboxylic acid. Now, the effect varies. So what we have to do here is that we have to know the compound we are talking about in the product, right? Now, if it's oxalic acid and you heat it, you are getting carbon dioxide, carbon monoxide, and water. This is fixed. You can't change it. So you learn it. Malonic acid, upon heating, you get carbon dioxide and acetic acid. It is fixed. Good. Now, succinic acid, if you heat it, and glutaric acid, they behave in the same way. Now, what will happen here is intramolecular dehydration. So within the same molecule, there will be loss of water from one molecule. So in the same molecule, there's intramolecular dehydration. And so this molecule, this part will lose hydrogen, this one will lose OH, right? And then that will form water as a byproduct. And then there will be coordination between this. That is what has happened here. That is what has happened here. So there's coordination between this. But in actual sense, that is not what is happening, because we have a carboxyl group like this, right? And then we have another carboxyl group like this. So what is happening is that this OH has been lost, this H has been lost, and there's coordination between this oxygen and then this carbon. So this oxygen is connecting this carbon and this carbon. That is what is actually happening at the molecular level. This is what we call the succinic anhydride, right? So intramolecular dehydration. That's the same thing as I've described here as okay here. That's if you heat glutaric acid, you are forming glutaric anhydride, intramolecular dehydration. Then we are saying that from glutaric acid onwards, that is, if you remove glutaric acid, all the other higher that can molecular dehydration, two of these, what will happen is that one molecule will lose hydrogen, the other one will lose OH, right? And so you would form this polymer, right? You form this polymer. The polymer is acetic acid anhydride polymer. So you realize that there's an acetic acid anhydride. That's an acid anhydride, sorry, appropriately, an acid anhydride functional group there. An acid anhydride functional group. So that's the polymer you would form if it's higher that upon heating. Good. Now, talic acid. So effect of heat on talic acid. Now, if you heat talic acid, you form talic anhydride. So the same intramolecular dehydration. Loss of hydrogen from one of the species, and then loss of OH from the other species, right? Very simple. Then when you heat, this is very specific for adipic acid. That is, if you heat adipic acid in the presence of barium hydroxide, manganese carbonate, or oxygen, right? Now you would get pentanone, very specific, carbon dioxide and water. So when this one comes up, this is what we are getting, very specific, right? Good. Now, the next one, cyclic imides can be prepared by heating ammonium salt of dicarboxylic acids. So if you add the ammonia to the succinic acid, right, as has been shown here, there's a normal acid-base reaction that will occur, but upon heating, you get your succinimide. You get your succinimide. So we are saying that you can form cyclic imides. Imides is when we form that's when we have an imide, but the nitrogen is quite secondary. So nitrogen is bonded to two different carbonyls, two different carbonyls. So that's an imide. It's not an imide, it's an imide, secondary imide. Now, an exercise for us to try our hands on. So we have steps. They ask us to show the steps, right? We are taking O-xylene to phthalic anhydride. So the first thing, what we have to do is that we have to oxidize. So we can oxidize this with chromic acid or KMNO4. We'll get our dicarboxylic acid, and then we heat. When we heat phthalic acid, we'll get phthalic anhydride. Very simple. So that's what has happened here. Very simple. Good. Now we have come to condensation polymerization. Condensation polymerization. Good. So we are asking ourselves, what is condensation polymerization? And we are seeing polymers are compounds that are made up by linking together small molecules called monomers, right? Now, in condensation polymerization, two different monomers come together, so they are added together. So we are adding smaller monomers to form larger compounds, right? And then there's a loss of another small molecule. So that is condensation polymerization. Right now, we are saying the monomers usually have the same functional group at both ends. So it's either they are diamines, they are dicarboxylic acids, or they are diols. And I think condensation polymerization may be formed by a reaction between dibasic acids and diols, between dicarboxylic acid and diamines, or between amino acids. So we'll talk about all these ones as we go along the slides. Now, some simple matching for us to do. So the first one here is adipic acid, D. The second one here is ethylene glycol. The third one here is diaminohexene. Then the last one is terephthalic acid. Good. So reaction, polyimide. Important things for us to take note of. A polyimide is formed between a reaction of dicarboxylic acid and a diamine under appropriate conditions, right? So this is the adipic acid. This is the diamine. And so what will happen is that the adipic acid will lose OH. So this is showing how they form a dimer. Will lose OH, right? And then the amine will lose hydrogen. So there will be connection between this nitrogen and this carbon of the carbonyl, right? And that is what has been seen here. This is the imide one. And then he has joined the two molecules. So this is the dimer form with the loss of a smaller molecule, which is water, right? Good. So that is that for this one. Now we are saying that when this is formed, you realize that there's still another carboxyl group here, and there's still another imine group here. So in the medium, if we have another imine, it can come and react to this terminal. If you have another carboxylic acid, it can come and react to this terminal, and that will elongate the whole chain. That is what we have polymerization. So it goes on and on. Another one will come and add, and then so dimer, trimer, tetramer, and then we go like that. Right. So monomers can continue to join by the imide linkage to form a longer chain. That is what we are talking about here. Good. Now, example, 1,6-hexene dioic acid can react with 1,6-hexene diamine with heat in an industrial process to form polyimide called nylon. So they are talking about an example of a polyimide, which is nylon. Now, nylon can be formed. That is nylon 6,6. The one used in this example is nylon 6,6, right? That's hexene dioic acid and then hexene diamine. Good. Now, let's look at how the reaction proceeds. So this is the hexene dioic acid, 1,6-hexene dioic acid, and this is 1,6-hexene diamine. Now, what will happen here is that the OH here will be lost, so we'll lose this OH. Now, the nitrogen has two hydrogens, so one here, one here. One of the hydrogens will be lost, so there will be a connection between this nitrogen and this carboxyl group, right? And that is what has been shown here. That is one has been shown here. So this hydrogen is still here. That is the one here. Good. That is what has been shown here. Now we are cutting the ends because this hydroxyl can also go and react. And then usually what we draw is just a small segment of a bigger polymer. So we are showing the dimer as a segment. So what happens is that we will cut this OH off because it can also go and react. And then we will cut one of the hydrogens off from here. So the hydrogens are two. Because we know one hydrogen will definitely go in a reaction, we'll cut one of them off. And then we'll put the square bracket around it. So this is how we represent a segment, right? We make sure the bond also cuts the bracket. That is how we represent a segment. And depending on the number of the moles of the compound here, that's the redetermining one, we'll get the number of water molecules being formed here. Very simple. Very simple. Good. So nylon products include hosiery, parachutes, and roofs. Now, reactions. So we are saying that nylon are a family of polymers, the members of which have different properties. Good. Now, this is another different family of nylon formed from aromatic compounds, right? So this is terephthalic acid reacting with 1,4-benzene diamine. 1,4-benzene diamine. Now, the same thing will happen here. So the OH here is lost. One of the H's here is lost. So hydrogen has 2, and nitrogen has 2 H. One of the H is lost. There will be a direct coordination between the nitrogen and the carbon here. And that is what has been shown here, right? Now we'll also cut the OH from this end. We'll cut one H, one hydrogen from this end, and then we'll put the square bracket around it. So the square bracket will cut this, right? Good. And this is clever. This is Kevlar. Kevlar. Good. So other commercially available one. Now, when you see nylon 4,6, the first number shows the number of carbon in the imine. The second number shows the number of carbon in the dicarboxylic acid. So this one will mean that we have 1,4-butane diimine, right? Butane, 4 carbons. Then this one will show that we have hexane dioic acid. That's 1,6-hexane dioic acid. Very simple. Sometimes you realize that we have only one number. So only one number also has a meaning. It means we have a ring. One of them, that's specifically for nylon 6, we have caprolactam. Caprolactam is a cyclic imide. So a cyclic imide. Let me attempt drawing it. Good. So something like this. So this is it. So this is 1, 2, 3, 4, 5, 6. Okay. So this is caprolactam, right? This caprolactam is a starting material. Now it's a single compound, but then when it breaks, it will break like this, and then it will get this carboxyl and an amino end, which can join each other, just as we have here. So we have nylon 6 formed from caprolactam. Now there are other ones. Good. So if you see 6,12 like this, the 6 is the imine, the 12 is the carboxylic acid, right? Now we have nylon 11, that is lurolactam, from lurolactam. Then we have, nylon 12 is from lurolactam, that's lurolactam. And then nylon 11 is from 11-amino and decanoic acid. Very simple. So now there's a question here that will be of interest to us. That is why, which is preferred, polyamide containing aromatic or aliphatic. Now, usually we prefer aromatic because it is stronger, right? It is stronger, it has higher strength, it has higher stability, and it has higher heat resistance, right? So aromatic will have better properties than the aliphatic ones. Very simple. Next up, polyesters. So we have to note that polyester is formed between dicarboxylic acids and diols. So diol is 2 alcohol, and that's 2 hydroxyl group, then dicarboxylic acid. So this is what we have. Now what will happen? The OH here will be removed, the H will be removed from here, will form water. Then there will be direct coordination between this oxygen and then this carbon, the carbon of the carbonyl, right? Good. So this is how the dimer is formed. Now, when the dimer is formed like this, there is still this acid functional group here. There is still this alcohol functional group that can react with other acid and alcohol in the medium, right? And so we see it can continue, react with itself and continue and form a longer chain. That is what we are talking about with regards to this one. So that is what is here. Good. Now, example. So we have a reaction between terephthalic acid and ethene diol, right? Good. Now, what is happening here? This OH is being removed. This H is being removed. So there's coordination between this oxygen and this carbon here. That is what has been shown here. That is the ester functional group that has been shown here. Now, we know that this OH group can go away. That is in the next reaction. So we cut it off, right? Now we know this H can go away, so we also cut it off. So remove the H, remove the OH, and then we draw the segment. This shows a smaller segment within a bigger chain, that is within a bigger polymer, right? Good. So now what we form here is PET, polyethylene terephthalic acid, and we are saying that it's used to make soft drink bottles. Another exercise for us to try our hands on. Now, we are saying that it's indicated reaction involved and show the structure of the following condensation polymers obtained from the indicated reactant. So nylon 6,6 from adipic and hexamethylene diamine. So we have to show nylon 6,6, nylon 6,6. Good. So nylon 6,6 has already been shown in the slide. This is nylon 6,6. So this is nylon 6,6, right? Good. So nylon 6,6, even without telling you, know it is from adipic acid and hexamethylene diamine. Because we've told you that the first 6 is for the amine, the carbons in the amine, the second 6 is for the carbons in the dicarboxylic acid, right? Good. So this is what has been shown, same as the one in the slide that we discussed. Good. Now Kevlar. So Kevlar is 1,4-benzene dicarboxylic, that's terephthalic acid, against 1,4-benzene diamine. Right now, we have also seen that one in the slide. We've seen that one in the slide. They asked us to draw the segment. Now, this is the segment as seen in the slide. If you can't draw the segment, you can start from the reaction and then produce your product as a segment, right? And just write the segment for them. Good. Now, PET, we are asked to draw the structure of PET. This is the structure of PET. They have given us a starting material. So even if we don't know, we can take it from the starting material to get our PET, right? Now, the next statement, dicarboxylic acid have 2 dissociation constants. One for the initial dissociation of monoamine, and the one for the second of diamine, right? The second into a diamine. Now, oxalic acid, the K1 has been given, the K2 has given it. Why is the K2 so much less acidic? It's so much less acidic because after the K1, the anion form is stabilized by a hydrogen bond. That is all. Right? So it becomes more difficult, it becomes more energy to remove the second hydrogen. Now, they have asked us to isolate the monomers, right? Isolate the monomers. Now, when you are given such a question, the first thing that will interest you is find either an ester bond or an imide bond. So this is an ester bond, it's of interest to me. This is an ester bond, it's of interest to me. There's an ester bond, it's of interest to me. There's another ester bond, which is of interest to me. Good. Then I will think about how the ester bonds are formed. Usually, one compound loses H, the other one loses OH, right? The one that loses OH is bringing C because it's always C double bond OH like this. And the other one has H. That is in the case of ester. So one loses OH, one loses H, right? Now, the one that loses OH is bringing the C, the one that loses H is bringing the O. And then the bond is formed like this. So the bond is formed C double bond O. So when you see the ester functional group, realize that this one here, the oxygen is coming from a different group, and then the C here is also coming from a different group. So that is the point where I will cleave the compound. So if I stand here, I'll cleave the compound here, and I'll cleave this compound here, right? Good. In the same vein, I'll cleave this compound here, and I'll cleave this one here. Now, if you look at it very well, you realize that this part is the same as this one. So I'll just choose one of them. I'll draw it out. I'll have my benzene ring here. So benzene ring, sorry, bad drawing, sorry. Good, benzene ring here. Then I have this. So this. Good. So that is what I have here. Then at this side too, I have double bond this, and then this. I've cleaved it so I wouldn't see this side. Now I realized I told you that this one is coming from the acid, so I'll put the OH back here. I'll put my OH back here. So I'm getting one starting material. Now, if I supposed to isolate this middle one too, I would have O, right? I cut it. So sorry, I cut it. So I'm still cutting. Then I'll put my H here because that's where we lost the H, and I'll put my H here. So I get my ethylene diol. Ethylene diol. Very simple. Very simple. Good. So that's what has been shown here. The next one that we are supposed to show. Good. Now the same thing that I'll do. This is an ester. So I'll isolate my esters and cleave them. So I'll cleave this ester here. I'll cleave this ester here. I'll cleave this ester. So between the C and the O, I'll cleave it here. I'll cleave this one here. So those are the only ester bonds. I can't write something from this one necessarily because this is not exactly complete. Even though I can isolate that one too, but it's not really complete. So I'll start from here, right? I'll write this one out. So I have dash coming up, coming down, coming up, coming down. So there's double bond O here, there's double bond O here, right? And then there's this one there. I'll maintain it. Now because I have cleaved it, and then this is the C double bond O. I know there's OH here. Then I know there's another OH here, right? Now let me write the next one. I have oxygen, so there's a bond coming. Oxygen, up, now up, oxygen. And there's CH3 here. I write my CH3 perfectly there. So this is H, this is H. We have already said that coming from the oxygen will lose hydrogen, the one that the alcohol will lose hydrogen. So once you have O there, just O there, you add the H to it. Now, if you come here, you have coming up, coming down. So this is my benzene ring, right? 1, 2, 3. So double bond O, double bond O. I will add my OH, and I'll add my OH. Very simple, right? Good. That is that for that. Good. So these are the three that I would get. These are the three that I would get. And then they have been named. So we have to take note of the names too down there. Good. Now the next set of questions asking us to find a product, right? They have given us a product. They want us to draw it out. So the first one, oxalic acid, and then ethylene glycol. Now this will give me a polyester. So polyester. If you look at it very well, you can just know your polyester. So this one, this formula that has been written is for this segment through this double bond O. So that is it, right? This is my oxalic acid, and this is my ethylene. So that is this one. You can just follow the example and get through. Succinic acid and heat. So this is something fixed, right? We said you form succinic anhydride. So if you have your succinic acid, succinic acid is 4 carbons. So H2, H2, COO, H. So what will happen here is that one hydrogen will be lost. So I'll lose this hydrogen. I'll lose an OH from here. I can just coordinate this. I mean, the slide, this was how they wrote it, oxygen joining the two. But in actual sense, we know that all happen is CH2, CH2, C double bond O, C double bond O. So coming down like this, plus water, right? He didn't even ask us to write the water. This says we should write this one out. So we can just write it out for them. The last one, the formation of dacron, right? A polymer. Now we have terephthalic acid and then ethylene glycol. So terephthalic acid, ethylene glycol, the polymer I'm getting, my square bracket, very important. So, and my benzene ring will come. So terephthalic acid, that's para, right? Good. Then this is C double bond O, O, and ethylene, O. So that is it, right? Very simple, very simple. Good. Then next exercise, they are asking us to provide the names, right? So we can count 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 is hexene. On the third carbon, we have methyl. So 3-methyl hexene dioic acid. Very simple. The next example we have here, this is okay, so it's metathalic acid, right? That's isotalic acid. That is what I wanted to say. Good. But it's benzene 1,3 dicarboxylic acid. Benzene 1,3 dicarboxylic acid. If you come here, we have 1, 2, 3, 4. So 2 bromo benzene, 1,4 dicarboxylic acid, 2 bromo benzene, 1,4 dicarboxylic acid. And the last one here, 1, 2, 3, 4, 5 pentene dioic acid, pentene dioic acid. Good. Now they have asked us to draw write the structures for the following. Right, write the formulas for the following. So this is butene dioic acid, and then ethane dioic acid will be oxalic acid. So this one, ethane dioic acid. The answer for this one is also here. We can just go back to the slide and then refreshing our memories on this. Good. So all too soon, we have come to the end of dicarboxylic acid. We'll make other videos trying to explain hydroxy acid. Now, let me remind us of these precautions. This is an alternate material. Sorry, this is a supplementary material, not an alternative material. Very important. The next thing is that if you have any challenge, you can see any member of the GPSC Academic Board for further clarification. Thank you very much and all the best.